So in fact, you see the set of discontinuities is, it's a countable number of discontinuities, and it's continuous everywhere else. Okay. Here the set of discontinuities is uncountable. It's everything, right? But it's what's interesting is where it's discontinuous and where it's continuous doesn't have to comprise an interval. Yes, Jenny.
Is there a function which does it the other way around, which is like continuous on all continuous on all rationals and discontinuous on all irrationals?
Oh, interesting. What do you think? Interesting question. So the question was, is there a function that is continuous at all rationals, but discontinuous at all irrationals? What do you think? How many people say yes? How many people say no? Oh, so now you've changed your mind, Jenny? Very interesting question. I'm going to let you mull over them, and I think you'll have the tools to answer this question very, very soon. Okay. Interesting question. Okay. So let's learn something about discontinuities. Maybe it'll shed some insight as to what's happening. So we can try to classify discontinuities. So if you have a function, let's say from an interval into the real numbers, let's make a notation. Well, I mean, here's one kind of discontinuity you might have. You might have one that looks like this, sort of a jump discontinuity, right? It's a very simple kind of discontinuity. Okay, at say some point x. And maybe the value here is q, and the value here is q prime. Okay. So notice in this picture, if I were trying to describe what's happening here, it's certainly the case that if I were in between, let's say, if I were in this, if I took some sequence on the right here, and I followed the images of these points, the TNs, what's going to happen as the sequence here, the sequence of points converges to x, to the images? What's going to happen? Yeah, it'll approach Q, so we can actually give this thing a name. So notice that for all sequences Tn in, let's say, x comma, okay, let's call this A and B, in x comma B, with Tn converging to x, we have f of Tn converges to Q. Okay. So we'll give this a notation. We'll say here, we'll write, one way to say this is f of x plus, we'll let that be Q. In other words, this is saying that the limit as t approaches x, but from the right-hand side, that's another notation, t going to x plus, of f of t is Q. Okay, so we'll have a notation that says, describes what's happening here. So this thing actually has a right-hand limit, but it doesn't have a limit. But if it has a right-hand limit, then we'll use this notation. And similarly, we can say from the left-hand side, I won't rewrite everything, that f of x minus, I'll say is what? Maybe q prime, which is basically what I mean to say here is as t approaches x from the left, f of t is also q. Q prime, excuse me. Okay. Okay, and of course the point of our discussion earlier about limits is that the actual limit, t goes to x of f of t, exists if and only if what's true about f of x plus and f of x minus. They're equal. Excellent. Okay, so that's just restating something we said before. So if these things exist, so if these exist, we'll say that this function has a discontinuity of the first kind. Yeah, so if these exist but not equal, we'll say f has a discontinuity of the first kind. Sometimes people say a simple discontinuity. Okay? Yes?
Do people ever write an equivalent, like, would you ever use like half delta balls to talk about this, or people always talk about it using sequences?
Oh, I only chose sequences as a way of thinking about this. You could certainly define it just in terms of the usual notion of limits on a half ball. Yeah, that's fine. Yeah, okay. And if it's discontinuous but not of the first kind, then we say it's of the second kind. Okay, good. So else we say second kind. Okay. So one question you should ask yourself is, are there discontinuities of the second kind? Yes.
What if it's one of those where the limit exists, but the point to which the limit is going to is not? So if you have a function and say f of x is q, but the limit as it goes to x is q prime from both sides?
Yes. Yeah, so if it's like this, right? Yeah, actually, this should still be included as first kind. I guess. Thank you. This is actually what I get for departing from my notes. So they could be equal, but the function value could be similar. So let me correct this the way I have it in my notes. So if f is discontinuous, there. But f plus and f minus exist, but f of x plus and f of x minus exist, then we'll say f has discontinuity of the first kind. And that will actually include, thank you, that will actually include this picture. Because on both sides they exist, but it's still discontinuous. Okay? Thanks. Yeah, basically we want first kind to mean kind of a silly kind of discontinuity. Okay. Okay. So what about other kinds of discontinuities? Are there discontinuities of the second kind? Well, of course there are. Otherwise we wouldn't have a terminology for this. But what's an example where, give me the condition that would have to be true to be a discontinuity of the second kind? Maybe the limit doesn't exist, right, on either side, right? So here's an example. You can have an example like this, and so here's the function from R to R. On one side it's doing something like this. Other side it's doing something like this, a topologist sine curve like last time.